Greetings. Gas turbines are one of the most important power generating systems around. Most aviation power depends on jet engines, which are an advanced form of gas turbines. Electric generation also strongly depends on these systems. Steam turbines these days depend on gas turbines for heating their boilers in combined cycles. Brayton cycle is the basic theoretical cycle for these systems. Different variations of the Brayton cycle are introduced in textbooks where their implementation depends on the application. We shall test a few of these variations in the present problem. Why do gas turbines produce power? Like any other power generating system, they use a simple thermodynamic fact. And the idea is this, that if we draw this diagram, this is the TS diagram, and if we draw the constant pressure lines, they are slightly bent. This is, say, P1, and this is, say, P2. Now, control volume work may easily be calculated from the equation W equals Cp0 times T2 minus T1. For an adiabatic system, this is work from the first law of thermodynamics. So the temperature difference, in fact, here means work. And the shape of these lines are such that as the temperature increases, the distance between two constant pressure lines increase. So what do? We compress in 1, 2. We compress in 1, 2. Then we heat in 2, 3. So then we heat in 2, 3. And then we expand in 3, 4. Expand in 3, 4. And the work gained from expanding this medium, which is usually air, is larger than the work initially required for compressing it. And the difference means useful work. So the work resulting from expansion of the hot medium usually air or combustion products, is larger than the work required for compressing cooler medium. And the difference is useful work. So it's a very simple idea. And the closed cycle, Brayton cycle, just closes this match. I mean, it says, just assume there is air, Air is compressed from 1 to 2, is heated from 2 to 3, and then it is expanded from 3 to 4. And the difference gained from work between 3 to 4 compared to the work required between 1 to 2 is the useful work that we gain. Now, uh, usually the problems for gas turbines give us a few data which are very classic and very practical. Now, the initial point is where do we start? It's usually ambient air. So our present problem tells us that P1 equals 100 kilopascals, which is about 1 atmosphere, and T1 equals 0 degrees C, which is a fairly cold ambient. Anyway, we have to know what is the temperature and pressure of the air that enters this system. Another limit, very important limit for these cycles are T3. T3 is important since it is the hottest point in this system, and therefore the turbine blades should bear that temperature. Uh, that is a technological limit for gas turbines. And the present problem tells us that T3 equals 1500 kelvin. 1500 kelvin. Now, between these two um, temperatures, which one is T1 and one is T3, there could be many alternatives. You see, if this is T3 and this is T1, different pressure ratios are possible. As extreme alternatives, assume that we compress air to a much higher value than expected, heat it up to that T3 temperature, and then expand it. Since these two lines are very close together, compression and expansion, not much useful work we would gain. On the other hand, if we don't compress it that much, it would be such a higher pressure, and this would be our expansion, and this would be our compression, and there would not be much useful work. So there is an optimum for useful work here, and usually problems tell us where they select that optimum to be. And here, this problem tells us that P2 over P1 equals 8. And that's the selection they have selected. In fact, uh, as the technology today is concerned, 1500 kelvins is a good temperature for turbine entry temperature. The pressure ratio could easily be around 20 or 23 for that T3 temperature. So this is a lower pressure ratio, this is a high temperature. That is um, not, we don't expect to get maximum work from the configuration that we see. A larger pressure ratio could well give us more work. Now, this is a very simple view of a gas turbine. This is the compressor, this is the combustion chamber, This is the turbine. Compression happens here, heating happens here, and expansion is in the turbine. Now, to simplify the idea, what we do is to just draw a line like this with a smaller area towards the end and call this the compressor. This is the in and this is the air going into the compressor. We usually denote combustion chamber as two lines which are just follow the can inside the combustion chamber, and this is the turbine which somehow is expanding, and we show it as an expansion. We connect these two with a shaft, which just shows that this turbine is running this compressor. This is what is called the gas generator. And the exit gas from this turbine has both pressure and temperature, and it's quite good for producing work. So usually they place another turbine here to take work out of it, or they just speed this air to higher velocities in jet engines. So this is how we show a gas turbine. Now I would do the same here and draw it that there is a compressor. There is a compressor where air enters it, and this is P1 and T1. The outgoing air goes into the combustion chamber. Usually they show it with CC, and this is point 2, this is point 1. Then the air out of the combustion chamber goes into a turbine where it expands, and there is a shaft between them which helps run the compressor. This might be one turbine which just runs this compressor, or there might be a larger turbine which, in addition to running this compressor, it also runs a generator and produces, say, electricity. So this is the generator. And in this larger turbine, then this is 3, and the exit flow from this turbine would be 4. So this is generally the different ways that we represent that real gas turbine that I just showed you in a sketch or in a TS diagram. In order to analyze different processes of this cycle, I've just redrawn my cycle and try to simplify all our governing equations for the cycle. You see, this is the mass conservation law, this is the first law of thermodynamics, and this is the second law of thermodynamics. Now, our cycles are usually steady. It is a cycle and it continues. The gas turbine produces power for as many hours as we require. Sometimes days and sometimes months. They work without stopping. When it's used in aircraft, except when we start it and we shut down, then it is working regularly, and at cruise conditions, it works in steady state. Brayton cycle and basic cycles are all defined at steady state. So to simplify these equations, these three equations, we have to put these values on the left-hand side to 0 because our problems are steady, and then try to simplify whatever there is on the right-hand side for each system. Now, I will do it one by one and see how it would result. As for the compressor process 1, 2, what do we have? We have 0 for mass conservation law equals m dot 1 minus m dot 2 in and out. Now, we usually, for the simple cycle, we ignore changes in velocity or elevation, and the first law of thermodynamics would be as 0 equals m dot 1 h1 minus m dot 2 h2 and minus w dot, and dividing everything by m dot, which is constant here. The first law would be 0 equals h1 minus h2 minus w. And further simplifying it, it means W compressor work for each unit mass would be Cp0, assuming perfect gas, which gas turbine cycle is defined for gases. It would be Cp0 times T1 minus T2. And that is the uh, work for decompression. You see, T2 is larger than T1, so this equation would give negative work, which is true, since you have to do work on the compressor. The second law would be as 0 equals m dot 1 s1 minus m dot 2 s2. There's no heat transfer. We are assuming um, the process, the compression process, to be adiabatic. And since for the time being we are assuming the compressor to be reversible, then this is how it would end. And since S1 equals S2, then we could use the equation T2 over T1 equals P2 over P1 to the power gamma minus 1 over gamma, which is the isentropic process, which is valid for the isentropic process. Now, for the combustion chamber, for the combustion chamber, again, the mass conservation would be 0 equals m dot 2, which is the incoming mass, minus m dot 3, which is the outgoing mass. The first law of thermodynamics would simplify similarly. It's only the case that instead of work, we have heat transfer. So what we would get is that 0 equals H2 minus H3, which is the incoming uh, enthalpy, outgoing enthalpy, and plus Q, which is Q, say Cc, which is the heat added in the combustion chamber. You see, heat would be positive since it's being added, and H3 is larger than H2. Well, the second law of thermodynamics is 0 equals m dot 2 s2 minus m dot 3s3, that is the incoming entropy, outgoing entropy, plus q dot over T E, which is the heat added, which where there is heat transfer, so there is some added heat. And if we assume that this heat addition is reversible, then estrogen would be zero. Well, we don't use this equation much, but still we have to write it. Now, for the process 3-4 or 3-5 or 4-5, which is for the turbine, depending on if we have a single turbine, two turbines in series, or a single large turbine, depending on how we look at it. The process 3-4, which is the expansion in turbine, what do we have? For the expansion, still 0 equals m dot 3 minus m dot 4. 0 equals, as for work, h3 minus h4 and minus w turbine. We usually call this turbine high pressure and this turbine low pressure for the reason which is obvious. So this is the high pressure turbine. And the second law would be very similar. I mean, S3 equals S4, and therefore T3 over T4 equals P3 over P4 to the power gamma minus 1 over gamma. And that is the expansion in the turbine. We may write a very similar equation for process 5-1, but in most gas turbines, in fact, quite a lot of gas turbines, almost every gas turbine, the air from 5 is thrown away and fresh air comes in from 1. So, in fact, we usually don't take that into account. But it's important because although it's not used in the gas turbine itself, I mean, in the real turbine, this is not recycled, but still, the gas going out of 5 is important because it is hot gas and it may be used in different instruments. For example, there might be a heat exchanger which uses hot gas here to heat the cold gas here. So we have to do less heat. We shall come to that point very shortly. And I shall continue with the rest of our calculation of the Brayton cycle or the gas turbine cycle in the next video. Cheers.